students. So in this lecture, we'll talk about band-to-band transition. Now, an electron rays from the top of the valence band to the bottom of the conduction band. So this is the conduction band, and this is the valence band. An electron is raised from top valence band to the bottom of the conduction band due to absorption of a photon in a direct transition. So when a photon strikes, so this is what is occurring, and this is a direct transition. And there is no exchange of momentum involved in this process. However, we can see that there is a small change in the K value. So this we can denote as, however, there is a small change in K vector due to the finite momentum of the photon. As there is a finite momentum, of the photon, and that finite momentum is h by lambda from Bohr's wave particle. Lambda is equal to h by p, so p is equal to h by lambda. Now, most 3-4 semiconductors, 3-5 semiconductors, we talk about 3-5 semiconductors, the wavelength associated with them is 1 micrometer. And so that is why if we say that p is equal to h by lambda, so the resultant momentum change is very small. So it implies the resultant momentum change is very small. And these are basically direct bandgap semiconductors, and typical example is gallium arsenide, indium phosphide. However, in indirect transitions, there is a large momentum exchange. Okay, so let's talk about indirect transitions. That is when we talk about typical silicon and germanium. Here, in these transitions, they are characterized by a large change in momentum. So when emission or absorption of a photon is involved, say that energy is say pH plus energy due to the photon exchange is equal to EGH, Eg, the band gap energy. So this is due to the photon and this is due to the phonon, the quantum of vibrations. Now, so a typical example of if you look into the directness and indirectness of the semiconductors, the EK diagram, the direct bandgap semiconductors are having the following properties. It's the conduction band, and this is the valence band. So their maximum of the conduction band and the minimum of the valence, maximum of the valence band and minimum of the conduction band are at the same k value. So there is delta k is almost equal to 0 here. However, in case of the indirect bandgap semiconductor, we can see a shift, or a shift, put it in a different way. So here there is a significant amount of change in K. So this is what is due to the phonon exchange taking place, that is due to the vibration. So whenever an electron from this point, whenever it rises up, it comes to this point, and after certain phononic transitions, it comes to the minimum. So it's like this to the conduction band, and after certain phononic transitions, it ultimately comes to the minimum of the conduction band. So this is a direct bandgap semiconductor like 3-5, and this is an indirect bandgap semiconductor like silicon and germanium. Now, in case of indirect bandgap semiconductors, that when we have written EPH, phononic energy plus photonic energy, is equal to the bandgap. In this case, the change in momentum delta K is represented as Kp, that means associated with the Cp. Where Kp is the wave vector of the phonon. Sorry, this is actually the photon, and this is actually the phonon, so it is associated with the wave vector of phonon, the vibrations. So therefore, an optical or an acoustic phonon with the right energy and momentum must be involved in a direct transition. Now let us do some problems. Suppose you have been asked to calculate the momentum change due to photon absorption in indium phosphide. There has been a photon absorption, and what is momentum change? That takes place in indium phosphide. The band gap of indium phosphide is 1.35 electron volt. And so the corresponding wavelength is 0.92 micrometers. We obtained this from the formula Eg is equal to H mu G is equal to Hc by lambda G. So lambda G is equal to Hc by Eg. So this is the wavelength corresponding to the band gap transitions occurring in indium phosphide. So this is of course a direct band gap semiconductor. Now the change in momentum or the kph, so the photonic exchange is simply 2 pi by lambda G. It is simply equal to, and it is in fact also equal to 2 pi by lambda ph, since there is no photonic transfer involved. So this is equal to 6.83 to 10 to the power 8 centimeters inverse. Now, in the case of an indirect band gap semiconductor, suppose the two values of momentum are k and k dash. That means this is the band diagram. The one which is involved in direct transition, that means had it been exactly in this place, the valence band, the conduction band, the energy involved for direct transition, if the energy say is E, and this energy is say E dash, or let's call it as E dash and E double dash. So E dash, which corresponds to direct transition, I can write E associated with K dash and so correspondingly it will be associated with wave vector k dash, and it will be associated with wave vector k double dash. So E k dash is simply equal to minus h cross square k dash square by 2 mh star, whereas Ek double dash, m star means effective mass. This is the effective mass. The difference between an effective, what is an effective mass? What is the difference between mass of an electron and effective mass of electron? Mass of electron is absolute mass, and effective mass is that mass when the electron moves through the different lattice points, positive lattice points, as it hops around, so its mass changes, so that mass is considered to be as effective mass, and when you take the effective mass in calculations of energy. Now, a similar manner, I will put it as Ek double dash instead of E dash and E double dash. It's Ek dash and Ek double dash. The energy associated with the direct transition is the band gap energy Eg plus the energy involved in the photonic transition. That means this lowering of this or the photonic phenomenon that is taking place. It will be h cross square. So k double dash square by 2me star. So energy of the absorbed photon EPH is actually the difference between these two energies. That means Ek double dash minus Ek dash is the one that is conservation energy. Now, such a transition will take place only when Ek dash level is tilted and the level Ek dash is empty. So, it is very important things that such transition will only take place only when Ek dash is tilted or I should say not tilted but filled. Ek dash level is filled and Ek double dash is empty. Again. So first the electron transfers from this to this. So, and from this transition requires this one to be in the empty state, and this is to be the full state. So this is what has happened. This is the Ek state, Ek dash state, and this is the Ek double dash state. So this is empty and this is filled. And also for momentum conservation, K dash must be equal to K double dash. It's called K selection rule. And K dash must be equal to K double dash. It's called K selection rule. If the photon energy or the photon absorbed is greater than the band gap energy, then that means if EPH is greater than EG, band gap energy, then electron and holes are not created with the same energy. Electrons with lower electrons will form with lower mass. And the semiconductors with these lower mass electrons are created, which have got than the whole. So, based upon these semiconductors are created with larger energy than the whole. So the only problem the problem is if someone asks you to calculate the energy of an electron and heavy hole. So there's a question to calculate the energy of electron and heavy hole. Produced by absorbing 1.5 electron volt photon by indium phosphide to find the energy of the electron and heavy hole. So indium phosphide, as previously said, has a band gap of 1.35 electron volts and reduced effective mass associated with optical generation. So as we have said that we have explained that if the energy of the photon is greater than the energy of the band gap, which is exactly happening in this case, the photon energy is 1.5 electron volt and the band gap is 1.35. So the electron will have a lower mass. So there will be a reduced effective mass associated with the electron. So it implies there is a reduced emistor. Now, how much will be that reduced emistor? It will be let's call that emistor as MR star, reduced effective mass. So 1 by MR star is equal to 1 by ME star plus 1 by MH star. Here's the formula. Written as clearly 1 by MR star is equal to 1 by ME star plus 1 by MH star. Now, EK double dash is again equal equal to E plus the difference between the ratio between the different masses, that is m r star by me star into the difference between the photonic energy and the band gap energy, E minus Eg. And whereas Ek star is equal to, again, the mr star mr star by m heavy hole star into E minus Eg. Now, the me star is given as 0.082 origin electron mass. The heavy hole mass is 0.085 rest mass, and the reduced mass is 0.075 rest mass. So, using this equation, this Ek star minus Eg we have written that Ek is equal to Eg plus mr star by me star E minus Eg. This was the solution. So Ek star, Ek double dash minus Eg. This value is obtained as 0.137 electron volts, whereas Ek dash is equal to minus mh, so mass star divided by m heavy hole star E minus Eg, and this is minus 0.013 electron volts. So you can also see that if you add these two, 0.137 and 0.13, so you actually get the EPH. So 0.137 into 0.013, you get 0.150. Now, the matrix element and the probability of an optical transition. We need to find out the matrix element. And probability of an optical transition. from first order time dependent perturbation theory. Uh, HO acting on wave function psi is equal to E k dash psi. Now this is the normal case where the direct transition has taken place. That means we are talking about this transition. So now at this stage we introduce a perturbation H1 in the form of light or EM radiation. So again this EK dash will now move to EK double dash. And can write Schrodinger's equation. There will be change in the Schrodinger's equation. So instead of, so initially it was H0 psi is equal to E psi. Now it will be H0 plus H1 psi is equal to E psi. And we know that E is equal to H cross del by del T. So just write H0 plus H1 psi is equal to IH cross del psi by del T. So the Hamiltonian involved, that is H k dash k double dash, this is simply equal to integration of sigma star k double dash H1 sigma k dash dr, and the k double dash minus k dash is equal to C, which is almost equal to 0. Now, when there is an absorption of a photon of energy H cross mu, the monochromatic photon flux monochromatic photon flux, call it Fi is equal to mod of S by H cross mu, and the unit is photons per centimeter square per second. There is a number of photons per unit area per second. It is incident. This is the photon flux is incident on the semiconducting crystal. At so S is the radiation energy per unit area per unit time, and it is also popularly known as the Poynting vector. Now this is the incident flux, Fi. What about the transmitted intensity when the photon is being transmitted by some transitions taking place from higher energy to a lower energy? So that transmitted intensity and the flux involved, we write it as Fd, and it is Fi minus a function of Ph cross omega d. Where d is simply the thickness of the sample. This is the sample thickness, and P is pH cross nu. This is nothing but the transition probability per unit volume per unit time. So transition probability per unit volume per unit time for allowed direct transitions, for allowed direct transitions. To explain pH cross nu in little detail, so this quantity Ft is, as I've said, is Fi minus pH cross omega by d. So this amount, this is the number of photons absorbed per unit time per unit area, normal to the incident light in a thickness d. So this is the number of photons absorbed per unit time per unit area. Normal to the incident light in a thickness d. So here this word is important, normal to the incident light and the thickness d. So if the light coming only normal to which, how much photons have been absorbed. This is this quantity P h cross omega into d. So we see that there is a with the increase in the thickness d, if we keep on increasing the thickness, there is a decrease in ft, and that decrease in ft can be mathematically written as ft is equal to s by h cross omega e to the power minus alpha d, where alpha is the absorption coefficient. Sorry, this is pH cross omega t. So if t is equal to s h cross omega minus s h cross omega e to the power minus alpha d. So we can take it as s h cross omega 1 minus e to the power minus alpha d. And for small, if this value is small, this alpha d value is very small. If small, then the equation simply simplifies to s by h cross omega 1 minus alpha d. So we can say that alpha h cross omega is equal to p h cross omega by s. Because if this is small, also this equation will also be affected. This will be p h cross omega d is equal to s by h cross omega alpha d. So that is once again. Initially was pH cross omega d was s divided by h cross omega exponential minus alpha d. So for small alpha d, this will be s by h cross omega alpha d. So this dt cancels out. We are left with alpha h cross omega is equal to p h cross omega by s. Now, in most 3,4 C5 semiconductors, a valence band is degenerate at the core center. submerged 3, 5 semiconductors. The valence band is degenerate. That means it has more than one energy stage. Only the one stage with the same energy.
Now, the effect of such degenerate bands contribute to the absorption. For example, for the heavy doped semiconductor, the absorption is
that means suppose there is a transition taking place. So this is a direct band gap semiconductor, and we associated with the band, and so instead of taking this as Eg, we will now consider this as Eg, the highest energy state in the conduction band. And this difference of the range is EF. So we can write the photon energy EPH as equal to Eg plus EF. Now with the variation of temperature, the variation of the absorption coefficient follows the variation of band gap. Now this by degenerate means that there can be also different energy levels. Some valence band, one can be like this. Now with the variation of temperature, with the temperature is varied, absorption coefficient also varies, and it follows the variation of band gap.